pleasure today to introduce Professor Miroslav Krstic.
University of California, San Diego.
San Diego, I know, but the way we pronounce your name is cautious. Krstic. Okay. He will also give a talk, I think, in the control seminar that comes after this. But right now, we're going to hear about neural operator for PDEs that stabilize PDEs.
Thank you so much, Professor Miroslav. So it's a great pleasure, great honor to be here, and the attendance must be required because I really wasn't expecting to see this level of audience. So thank you very much for coming here. I think I do have the understanding of the mathematical caliber of the audience here. So I want to tell you up front that this is a talk that I've simultaneously prepared both for this seminar and for a talk at a company called PhysicsX in London, which does serious development of commercial software for systems modeled by partial differential equations, namely serious users who are very talented in applied math and physics. And it's not that I was lazy to fine-tune this talk to the audience at LJLL. I thought it actually might be more fun if I emphasize more the intuition and de-emphasize the notation and other formal aspects of what I have to say. So let's let my estimation proves to be right. I will state a few theorems. I will try to get through them quickly so that I don't end up speaking about very, very few things in a ton of detail and sacrifice the breadth of possibilities that arise here. So I think there is no field of science in which machine learning and AI is not met with either fear or contempt, and of course with excitement as well. We spent lunch talking a lot about ChatGPT and how it can help us in research. My attempt until several years ago was to absolutely ignore it. And then I was put in the position to speak to a young audience of researchers who were in the midst of a transition from classical control theory to control theory influenced by data science and machine learning. And it was an incredibly discomforting experience because they expected I knew I had something to offer, which I had nothing to offer. And I survived, and then I had another big talk to give the body lecture at the Conference on Decision and Control, and I realized if I go with just PDs and theory, anybody under 35 will just yawn and think that this guy has wasted their time completely. So I decided that since I'm not retiring at 58, 59, and so on, that I really need to think about what I do, which is fundamental control theory for nonlinear and PD systems, can meet with these new possibilities. My plan was not to just forget about the previous 35 years, hit delete on control theory and switch to database stuff. I was looking for a way for machine learning to enhance what I'm doing rather than to replace what I've been doing. And I think I found it. So that's what I want to tell you about. Machine learning is one role of it is to develop mappings, to approximate mappings between certain inputs and certain outputs. And the role that I found for machine learning in control theory is the function of control theory, the function of model-based control theory, which converts models, namely differential equations with their parameters and functions, into feedback laws. So this is what I want to do. Not walk away, not forget about any of the heritage in PD control theory, but use machine learning for some enhancement. What kind of enhancement? Well, my title is, what was it? Using neural operators to approximate PDEs that stabilize PDEs. So to control PDEs, there are certain PDEs that need to be solved. And in some scenarios, these PDEs need to be solved over and over in real time. I'll get to that. So solving PDEs, another one, at each time sample is numerically pretty intensive. If machine learning can learn these mappings, which are operators, and offer 3-order of magnitude speed up. This makes a difference from turning PD control from being simply theorems, very, very nice results that we can't really implement, into things that we can implement and use. But these approximations, we don't want them to ruin the theoretical results. So I want to keep the certifications is the word that the computer scientists use as a replacement for the word proof. So I want to still have proofs of what I do and guarantees as I employ approximations. So neural operators, you've all heard about them. There is George Krstic over there. This is an idea that somebody brought to my attention maybe 3 years ago, that Krstic and other folks, I think I saw a poster with Andrew Stewart with a talk from 2023, I think maybe over there in that corner. So various people have been working on developing the theory behind the approximations of not nonlinear functions, but nonlinear operators. So the approximations of nonlinear functions goes back to the paper by Sibenko, which, by the way, was published. It's a neural network paper, but it was published in the Journal of Mathematics of Control Signals and Systems, edited by Eduardo Sontag, a control theorist. So this result on the universal approximations of functions got extended by two guys with the last name Chen in 1995. For operators with layer networks, it was a little noticed result until recently. The first theorems for deep neural network approximations started to appear for these function-to-function nonlinear mappings. So let me give you a fairly informal digest of these universal approximation theorems. I'm not an expert on neural networks. I'm not an expert in Krstic's or Andrew Stewart's fields. Just state something that holds for one particular class of these neural approximators of operators, but similar things hold for many different classes. So suppose that we want to approximate a certain nonlinear mapping from functions into functions. It's hard for me to see what my own slides. Maybe I should stand here. So no matter how accurately, no matter how small the error you want to achieve between the actual operator and its approximation G with a hat, there is a neural network, G hat, that achieves that error for all function inputs in a certain compact set, in a given compact set of continuous functions. This is an existence result. You might immediately say, what does an existent result do for a user? Tell me how to build this, or at least, how big the network needs to be, or how large the data set needs to be. There are results that answer those questions also. I'm not going to get into that because, my topic is control, and those results also are rather conservative. So you would immediately say, that's not very useful, these exponential estimates of the sizes of neural networks. So that field is in progress. I will just rely on the fact that the existence question has been answered. And the main condition is the continuity of the operator and the compactness of the set of input functions. So here's what I'm going to try to cover. I wanted to show you as much as I can, rather than as precisely as I can. I want to show you some results both for hyperbolic PDs, which are easier in this regard in terms of the use of these neural operators, and then for parabolic PDs where things get more complicated. And I want to show you results both for stabilization of PDs and for the state estimations of PDs, namely for stabilization of the errors between the dynamical systems that estimate the unmeasured state of the PD and the actual state of the PD. Then I want to really go to the online use of these methods, where I combine the offline learning with online learning, namely at each sample of the state, I solve again, or rather, I evaluate again the neural operator to give me a new solution for the PD. And finally, if I have time, I will show you something that is particularly interesting. It is infinite dimensional. It involves both ODEs and the transport PD, namely delay, where the things become applicable to robotics and really turn out to be useful. One thing that I forgot to say is that the way the neural operators were brought up to me was that somebody said, hey, have you heard of the work by Krstic and so on? They can produce the approximate solutions to Navier-Stokes at a fraction of the numerical effort, and you work on control of Navier-Stokes and so on. So yes, this might have originated from Navier-Stokes, but I'm going to be solving some completely different PDs that show up in the control of PDs. So I showed you at the beginning a diagram in which I showed a mapping from models into feedback. So the nonlinear operators that I'm talking about are operators that map functional coefficients. So I'm going to be mapping functional coefficients of PDs into functional gains in the feedback laws for PDs. I'm going to start in the simplest possible domain with the simplest possible PD, just an interval domain. X is the single spatial variable. This time is t. X is the spatial variable. U denotes the state of the PD. And I'm going to show you immediately an example of a PD that is unstable without control, and where you have to design a feedback law to stabilize that PD. The canonical difficult problem in stabilizing PDs is the problem where the control acts on the boundary. This is not universally true that those are the hardest problems, and that the problems within domain actuation are less hard. But these are never easy, that's for sure. Acting with a scalar input on instabilities that takes place in the entire domain where the control doesn't act. So now let me get a little more specific. I want to start with the simplest PD in which there is something to do for control. So this is the one-dimensional PD whose baseline is the transport equation, just at one derivative in time and one in space, but in which, in addition, there is a recirculation from the outlet, from the position x equals 0 of that transport process back into the everywhere in the domain. So you see this beta of x brings the outlet everywhere throughout the domain. And when that happens, you all know, even if you're not control people, you know about feedback. You know about negative feedback and positive feedback. Negative feedback is good, positive feedback is bad. Well, there is a positive bad feedback in here, which comes from the outlet and enters everywhere into this PD. This PD can get destabilized due to the presence of a term like this. Is this a toy? Not totally. There are some approximate models of traffic where the presence of routing applications introduces the risk of circulation of information and the possibility of destabilization. The full-blown traffic models, I'll get to that at the end. You will see the traffic, an actual traffic. So what happens in a model like this? This is what happens. Without control, when control, shown in red here, at x equals 1, so the control is applied at x equals 1, the outlet is at x equals 0. When zero control is applied, when you start from some constant initial condition, this is non-zero constant initial condition. This is what happens. You get instability. There's some oscillations in time, a little bit in space as well, and you don't want that. You want to kill such oscillations. The control is to be applied at x equals 1. The instability is being generated everywhere throughout the domain. This is what happens. This is the recirculation that comes back from the outlet everywhere. If the control could act at each point, then you would simply sever, you would cancel each of these these positive feedback loops, and you would stabilize this. That would not require any research. Doing it with control only here not only requires research, it even seems impossible, but it's possible. So how to unlink these feedback loops domain-wide while acting only here at the boundary of the domain? The answer to that is one answer that is particularly clear is the so-called backstepping design for PDs. And here's how it goes. It is inspired by the feedback linearization methods of the 1980s for nonlinear ODE systems. This feedback linearization method says that you combine two things. One is a change of coordinates, a change of the state, the transformation of the state, and feedback control, and you transform the system into a desirable form, which in the case of nonlinear ODEs is a stable linear ODE. So now I'm taking this same idea and elevating it to infinite dimension and introducing a transformation, and then at the end also control. The transformation that I introduce here, which happens to work for this class of problems, is Volterra type of transformation. A general Volterra transformation would be an integral transformation with a kernel K. So what I'm transforming is the state U of xt into a new state W of xt with a Volterra transformation shift. And a general one would have two spatial variables, x and y. It would be k of x comma y. But for the simple problems that I'm starting with, turns out that this kernel is a function of one variable. I want to start as clear as I can. So this Volterra transformation of the second line happens to be just a convolution. Once I introduce this transformation, the stabilizing feedback that corresponds to this transformation will employ this kernel function k, and the feedback law would be the feedback of the state, lowercase u of y comma t, with a functional gain k of 1 minus y. What I keep in blue is the thing that I haven't introduced yet. What is this function? Given beta, which appears in here, beta is the bad guy. What is my tool, k, to handle the bad guy? So the goal is to eliminate the bad guy, to delete it with a transformation in the feedback, and to impose a zero boundary condition so that in closed loop, we have just a transfer process with nothing feeding in. This is not only exponentially stable, but it is finite time stable. So the question is how to eliminate this destabilizing recirculation. If we can, then this is what we would obtain. We would stabilize the oscillations and we settle in finite time to the zero state. So once again, yes?
Why is the time going to 2 in the figure? I thought it was between 0 and 1 time.
It is very much possible that this simulation corresponds to a domain of the length 2.
Okay.
I've pieced together things from different students and so on. An excellent catch.
In case
No, in reality, it happens to in finite time. In exactly the same, the time corresponding to the speed of propagation. So the question is how to use this transformation to arrive here. And the answer to that question is very basic calculus that leads you to this relationship between beta, the coefficient that destabilizes the system, and k, which is the functional coefficient in the feedback law. Just take a look at this. For a given beta, this is a linear integral equation in k. But for a collection of betas, this is not a linear operator. It's a nonlinear operator from beta into k because of the convolution. And the easiest way to see it is just to take the Laplace transform in space x, and you see this nonlinear operation nice and clear from beta into k. So it's an operator that is not necessarily trivial, taking arbitrary functional inputs beta. Interestingly, this operator is the inverse of itself. But I don't want to belabor on that. That's just an elegant feature of the example. Doesn't generalize. So I'm not going to scroll back to Krstic's theorem, but Krstic says you can approximate the operator, that operator, with a neural network with an arbitrary accuracy, provided the operator is continuous. And if you have the Lipschitz constant, if the operator is Lipschitz and you have an estimate of the Lipschitz constant, I can give you an estimate of the size of the neural network and of the data set with which you can approximate the operator. So the first step in all of this research is to take these nonlinear mappings from the model into the feedback gains and to study these nonlinear mappings for their continuity and preferably also for Lipschitz. So the first basic result is that one can estimate the Lipschitz constant of the operator, of the nonlinear operator, in this way. It's a conservative estimate. And it's an estimate that depends on a bound, L-infinity bound, of all the input functions allowed and for which the operator is being approximated. So having met that condition of Krstic theorem, one can invoke the theorem and says that there exists a neural network which deviates, whose output deviates from the output of the actual operator by no more than epsilon for all inputs in a complex set of functions bounded by V. And in order to ensure compactness by the Arzellas-Foley theorem, for instance, I would restrict these functions beta to be Lipschitz as functions. The operator is Lipschitz, the functions being Lipschitz is a completely separate thing, just coincidentally sounds the same. All right, so one can approximate this operator. I'm not a neural network person. I'm not a machine learning person. I do have collaborators to whom this approximation is the most interesting thing. To me, the interesting thing is once I use an approximation and plug this into this very complicated feedback relationship of a PD with a control law, will I retain or lose the theoretical guarantees of stability? So once I replace the nominal perfect K by the output of the neural operator fed by the PD's functional coefficient beta and place that into the feedback law, which I'm feeding by the measured state U, will I achieve stability?
Excuse me, are you going to give the definition of a neural operator at some point? Because I didn't see it.
No, it's very complicated.
Okay.
It's very complicated. It's a deep neural, multi-layer neural network.
That goes from infinite dimension to infinite dimension, more or less?
Yes. Okay, so once I substitute this control law into the boundary condition of the PD that I'm trying to control and apply the Volterra transformation, I obtain a closed loop system in which there is no error in the boundary condition by construction, but there is an error somewhere. And it turns out that the error is on the right-hand side of the PD. Now you see that this error, delta, is vanishing perturbation. In other words, it's not going to change the equilibrium. It may, the equilibrium at zero. It may only destroy the stability of the equilibrium if delta is too large. So what is delta? Delta happens to be this function, which is not a totally trivial function because this operation minus unity plus beta convolving with this function, that is delta. But you will believe me that since I'm guaranteeing by the universal approximation theorem that this quantity will be smaller than epsilon for all beta for which the training was performed and for all betas that may arise in that PD system, that all of beta also can be made sufficiently small. You have to skip some details. This is a pretty believable detail to skip. So now, to prove stability in a Lyapunov sense, I need to perform several steps. I need to study the stability of that perturbed system using Lyapunov functions. Lyapunov functions for transport-dominated PDEs have been perfected, for example, by Jean-Michel in the context of Séminaire equations. This is something much smaller and simpler, but the same sort of spatially weighted L2 norm applies in here. And here's the key result. So the key result is that exponential stability is achieved, or I would say retained, because for epsilon equals 0, that's the basic theoretical result, provided the neural network is trained for epsilons that are small enough, and a conservative estimate of how small is small enough is given by this formula, which I've made as conservative as it takes for it to be easy to comprehend. So the accuracy of the neural network is in inverse proportion to the size of the destabilizing coefficients beta, which are bounded by beta. In other words, the more unstable the open loop system is, the larger the neural network that I need to survive the neural operator's error. And after that, I get to the main result. So the previous result, yes?
When you say the larger, it's just the size of the neural net or also the size of the data you need?
Both. So this is not the stability result. This is just a Lyapunov estimate. My original system state is not W hat, but it is that U. So I want to tell you what the main result is. So the main result is an exponential stabilization result given by this. This is in the sense of an L2 norm in space with some overshoot coefficient capital M, which if you really want to see it explicitly, it's there, it's conservative, but nothing here is non-explicit. This is. C star is also an explicit decay coefficient estimate. Now, I want to emphasize that this is not a result just for one system and for one approximation and for one controller. This is a result for all the controllers and for all the possible realizations of the neural operator, of which I'm depriving you the details because it's a different talk. So it's actually not just stabilization result, but a result on robustness to the realization, to the particular realization K hat of the neural network. All right, let me now move from hyperbolic to parabolic PDEs. In the first example, I have only one spatial variable in the mapping that I was showing you. It was a mapping of functions of one variable into functions of one variable, beta of x, k of x. All right, in parabolic PDEs, there are two derivatives in space, and all of a sudden, just a convolution in the backstepping transformation does not suffice. So now I'm considering potentially unstable PDEs whose instability is caused by the presence of possibly positive destabilizing reaction term in here. This is the simplest PDE, not the most general, but on the contrary. The simplest one I would choose for tutorial purposes where things are not trivial. So a reaction term causes instability, and this is going to be mapped into a control law. The instability in the parabolic case is far more boring than in the hyperbolic case. In the hyperbolic case, you saw oscillations. Here, it gets pretty boring, but it's pretty nasty as well. Things grow in an exponential manner without oscillations for this particular example system. So for the first example, I could get away with the simplest of kernels in the transformation. A kernel which is a function of only one variable, k of x minus y, whereas here it needs to be a function of two separate variables. To transform the system, this system, into a target system in which this term, the offender, this offending term disappears, and all that is left from the reaction diffusion equation is just a heat equation. For that to happen, this kernel K needs to satisfy three conditions, which I just want to show you one. There's a PD and there are two boundary conditions. I just want to show you the PD. So you see the PD that arises is this kind of PD. It appears to be some sort of a wave equation, but it's not really a wave equation because the domain is not rectangular, but it's triangular. Namely, space advances together with time, where time advances, the time-like variable x advances along with the space-like variable y. So everything that you know about wave equation, nothing that you know about wave equations applies here. This is a Bursa form PD. It's a very special type of a PD that you need to approach in a manner appropriate for that class. So now the neural operator needs to approximate a mapping from functions of one variable, lambda of x, into functions of two variables, k of x and y. So at this point, there's a lot to show, which I'm going to leave out. It turns out that because of the form in which the approximation error enters the closed loop system, one needs more than continuity of k. One needs an extra regularity. One needs twice differentiability, and that all needs to be incorporated into the study of the continuity of the operator from lambda into k and encoded into the approximation with a neural operator. It's a whole paper. I'm just skipping all of these details. I just want to give you a sense of what this approximator does. You see this shaky, rough-looking thing? That's what the neural network spits out when you put in a nice and smooth lambda of x, and it produces as an output this point. Here is the approximation error. If you're by any chance from the world of neural networks and you're interested in the accuracy and so on, it's shown here. It's about 10% error relative to the size of the output. Okay, so it's non-negligible error, but it's definitely an order of magnitude small. And if you're really a professional of neural networks and do machine learning for a living, I do have this one slide that tells you what, as of about a year and a half ago, these are outdated results now, what it takes computationally. So this hasn't changed. To train that neural operator, we use 76 million parameters, which is nothing extreme. We trained them on Chebyshev polynomials. It took 5 minutes on an NVIDIA chip for 500 epochs. And the computation of the output of the neural operator for each new input function takes almost an embarrassingly short amount of time on a GPU. You almost think, oh, this must be an easy problem, but the problem is not the hardest, but these things are incredibly fast. What if you don't have a GPU? Well, it might take hours to train and milliseconds to evaluate each new output. The theoretical result is structurally the same as before, namely exponential stabilization for a family of neural operators that all guarantee an error no greater than epsilon star, where for epsilon star we have an explicit estimate, and let me not belabor that anymore. You've seen me show this feedback law where some gain, which is computed with a neural network, is multiplied by the spatially distributed state of the system. And if you have a bit of an engineering background, you immediately know that there's no way you can measure a fully distributed state of the system. Maybe you can measure something at the boundary, you can measure something at some point in the domain. And I just want to tell you that is a whole separate subject, a fully tractable subject that is called, among control people, is called observer design or a state estimator design. Estimating an unmeasured state using measurements of only a portion of the state. So, for example, in the reaction diffusion equation, if you happen to be measuring only at the boundary, and what you measure is, for example, the boundary flux, you may measure, a boundary flow or boundary temperature. Doesn't matter if it's Neumann or Dirichlet.
I have a question about the previous part. So all of these formulations, they work quite nicely in the linear case, but
I'll get to I'll get to a nonlinear case. Yes, it gets it's you hit different challenges. This is my last few slides. Please bear with it. So if you don't measure, if you measure only the flux, this is how you estimate the entire state, and this is what happens. This is the evolution of the state under some open loop input at the boundary. And the point is that it's a non-trivial evolution of the PD state, and that this state estimator, after it catches up, doesn't matter if it catches up very quickly or it takes a while. After it catches up, then it follows subsequently because it has the model encoded into it. And the gains of this can be also produced using neural operators with guarantee. Let me now get to what really motivated me to look into computational power of neural operators. It is when you have to solve that kernel PD, not once offline, but you keep solving it over and over online, that the ability of 1,000-fold savings begins to matter. So let me go back to the transfer PD with recirculation one more time. But let now beta be a function that is unknown, and let me estimate in real time that unknown function using a real-time estimator beta hat that depends on an online estimator. This is a whole sub area of control theory called system identification and adaptive control. We know how to do that. I'm not going to try to squeeze in crash course on that into here. Just believe me, this is estimating, this is doable. The question is, as I estimate in real time, this beta hat, which is inaccurate, for quite a while, it's inaccurate. And if I feed this inaccurate estimate into a not perfectly accurate neural operator, neural network K hat, can I still survive in real time? Can I be stable? So in case you really won't accept just being told that we can estimate the unknown parameters of a PD, I just want to show you what one such estimator looks like. It's a non-trivial infinite dimensional dynamical system, infinite dimensional because the estimate of the functional coefficient is an infinite dimensional quantity. It's a spatial distributed of a space-dependent function that depends on time as well because it is estimated in real time. And if you look into this expression and its full definition with everything that goes into it, I just don't want you to really try to make sense out of it because it's complicated. Let me just tell you, it's infinite dimensional, but it's not a PD. It's an infinite dimensional ODE where there are integrals in space but no derivatives in space. And this structure comes out of a methodology that is based on the Lyapunov functionals and comes with guarantees itself when there is no neural operator. So here's how adaptive control works. If you apply no control, you already saw what happens. With zero control, that hyperbolic system oscillates towards infinity. When you apply control of the adaptive kind, this is what you get. And there's a lot in this plot that I want to break down. You see what happens in this plot. You recognize the tendency of instability. Then you recognize that at some point, this stability begins to be overcome, and then the system settles to an equilibrium. So there are multiple things going on in here. One is the controller, and the other one is the parameter estimator. The controller is doing its best with the estimate beta hat, but the estimate beta hat at the beginning is terrible. The true beta is this blue curve at time, is this blue curve. The initial estimate beta hat is constant. I say, I know nothing, I start with a constant beta. That's, let my estimator learn beta. So this estimator is used in the feedback controller, and the estimator is noticing from its own differential equation in this slide. The estimator is noticing that the control is doing a very poor job with the estimate that it's producing, and it's automatically adjusted to begin improving the estimate. You see that these estimates start approaching the blue, but they never perfectly approach blue, because that's not even neither possible nor necessary. The estimate gets close enough such that the controller is stabilized. This subject of adaptive control is just incredible. You never learn, you want to learn, you never learn perfectly, but you learn well enough to complete the task. I think from real life, this is a pretty common experience, that the perfect knowledge is neither necessary nor achieved. So back to the theory. What can we prove? So we can prove, and this is just for stabilization specialists, we can prove the upward stability in the sense of a class K estimate in the L2 norm of the state and of the functional parameter estimate. And in addition to that, we can prove pointwise in space, namely for all spatial points, that the state goes to 0 without necessarily the estimate beta head going to beta. The study of this is mathematically incredibly interesting, because there are so many bad things going on in parallel. If the problem was not adaptive, and if I was not using a neural operator, the closed loop system would just be the transport PD, and everything would converge to 0 nice and clean in time 1 with this boundary condition. But with the neural operator, there is its approximation error. With the parameter estimation, there is the error of the estimation of the parameter. And if that were not complicated enough, the fact that the parameter is being changed online introduces, as a third error, the rate of change of the parameter estimate. So it's really interesting, and it's really fun once you get to conquer this problem. It was conquered by a graduate student sent to me by Col Demin, usually with students from France. I think, what is the hardest problem I can think of at the moment? And, let's give it a try. I'll show you who that student is. Before I wrap up, let me now go from toys to something that is fairly real. Control of traffic. This is a very French topic. And what?
French.
It's French because the modeling of traffic started in the 1950s in the US. Traffic is, when you take it with many vehicles over a long enough road, it's natural to approximate in a continuum manner with a PD. Which PD remained an open problem for close to 50 years. Many candidate models were proposed, and they were almost all right, except that they were not completely right, because they were doing stuff that humans don't do at all, like constantly look in the back and worry about the driver behind me. Things were being approximated with gases. Humans were being approximated with gases. Finally, the right answer was provided by a couple of CNRS researchers, an advisor and a PhD student, I think maybe in Sofia Antipolis, and Russell. And Zhang is another researcher from the University of California, Davis, who in parallel came up with something very, very close. So the PD model of traffic is very much like, it resembles the model of gases. There are two states: the density of cars along the road and the velocity of cars along the road. All of us have, maybe we're not even aware of it, but we have a certain degree of comfort about the distance to the car in front of us. And there's a static map view of rho which says to which velocity we adjust the speed of our car depending on the density that we are experiencing of cars in front of us. So that is that model. It has certain boundary conditions. I want to de-emphasize that. And there's one thing that is unknown in all of this. There are several things that are unknown, but one of them is that nobody knows the so-called relaxation time, namely, over what time period, for how many seconds it takes us to adjust our speed to the speed that we consider comfortable at the given density rho. So this relaxation time is an unknown, and definitely it varies on different roads, among different populations, at different hours, at different weather and visibility conditions. So it's a good test case for adaptive control. This pair of PDs is very similar to seminal PDs of flows through canals. This PD is a special case of a class of couple first-order hyperbolic, nonlinear hyperbolic PDs whose stabilization was pioneered by Jean-Michel. So this is an application with neural operators and with adaptation piled up on top of what Jean-Michel did maybe 15 years ago, right? And it was even implemented in water cleanups. Yeah, I had it here. I forgot that I had added it. So in open loop, at high density, the car is going to stop and go. Stop and go traffic, you're familiar with that. It's below 40 kilometers per hour on the freeway. You are likely to experience stop and go, second, third gear, just frustrating, awful, dangerous. And the goal is to stabilize this. What's at your disposal to stabilize this? I'm not talking about brute force, commanding people to drive steady, don't be afraid, blah, blah, blah. No, there is, in order to command the speed, keep telling people, change to 38, no, go down to 36, none of that. There are conventional implemented ways to control traffic using ramp metering. So at the ramp that enters the freeway, there's a green and red light, and the duration of that green and red light is typically constant, but it can be varied a little bit so that you influence at the ramp point, influence the influx of the density of cars. Now, what's obvious is that by varying the red and green light duration ratio, you can influence the traffic downstream. What's not obvious and interesting is that you can do it upstream. And the way you can influence the traffic upstream is because every driver who is faced with somebody entering the road reacts to that. And every reaction in dense traffic goes to the driver behind the driver. And there is a wave that actually travels in the upstream direction. That's the interesting result. So once adaptive control is applied, these oscillations are stabilized, and this is done with a neural operator being applied at each time instant. Let me see. This is, I promised to bore you, and then I will show something nonlinear. So the fastest possible nonlinear thing. This is now an application to nonlinear ODEs, but with large delays. A delay is an infinite dimensional subsystem. It's the simplest of PDs, the transport PD. And to compensate delays in the control of unstable nonlinear systems, you have to solve in real time the differential equation for the system, which is written here in the form of an integral equation. That happens to be a nonlinear mapping from the control history at the time window, d time units in the past until present, and that mapping needs to be learned rather than being computed at every time sample. I will skip the details. This problem is solvable, and I really want to be frank about the pros. This is totally different from approximating gains. when you approximate gains, gains being a multiplicative quantity to the state, they do not change the equilibrium. The approximation can destroy stability, but not the equilibrium. Here, when we are approximating the predictor, namely the whole feedback law, the equilibrium is also altered. And there is no way that for arbitrary nonlinear systems that are not forward complete, that you can compensate the delay. So the result is a result that I called semi-global and practical. In other words, there's going to be an error as time goes towards infinity, which is proportional in the sense of a class K function to the approximation error of the neural operator. And the whole result is going to hold not for all initial conditions, but for a set of initial conditions that corresponds in a particular very precise mathematical way to the size, to the ball of initial conditions on which the predictor operator has been trained. Okay, let me not leave you with a dance theorem, but let me just, for the end, play this for you. This is something that comes out of the control talk that I will give. The goal is to park a car from that starting initial condition to right there. And this is not actually an easy problem to accomplish entirely by feedback. When there is a large delay applied at the driving and steering inputs, what happens is that the car gets completely confused. But with that feedback and with the neural operator, this is what is accomplished. And with that, I apologize for taking extra time and thank you for all your attention.
Thank you very much. Do we have questions or comments?
Yeah, but when there is some uncertainty on speed of propagation, is it possible also to use a method to estimate the speed?
That's a really hard question. That's the hardest uncertainty. So first, instantly you lose the ability for a global result. This corresponds to the problem that Delphine Bresch-Pietri worked on me 15 years ago during her summer in San Diego. When you don't know the delay, that's like the delay is the simplest form of a propagation speed. When you don't know the delay, how do you do that? The results cannot be global, but one can get local results. I don't like this problem because, you know, if the results are local in the state and in the initial error, then why don't I just simply use a small, slightly erroneous constant feedback? But that's the reality. These are the worst parametric uncertainties. And I forgot to acknowledge these people. The adaptive stuff was done by this fellow who's just starting his PhD at École des Mines. Rafael Vasquez spent a year with Jean-Michel Coron and is behind the things that were built so that ultimately traffic can be done. Mamadou Diagne earned his PhD at the University of Lyon with Jean-Michel on his committee, and I think that's the entirety of the French connections.
Other questions? Maybe online, people who are connected from remote.
Maybe make the result again for the nonlinear model, you get something semi-global that only works for a section of the circuit that is what we have. Can you explain?
Yes. So first of all, suppose that the system is where we have a nonlinear system, and suppose that it's forward complete. In other words, no matter what input you apply, the system will never go to infinity in finite time. This is needed because you have a long input delay. If the control doesn't reach the system before the finite escape, it's hopeless. So we're limiting the whole consideration to hopeful problems. But then, beyond that restriction of forward completeness, we also need to restrict the initial conditions still, because the neural operator cannot work for arbitrary large initial conditions because you would need an arbitrary large size of the neural operator. Since you're approximating the neural operator is a mapping, it's a mapping of two inputs into a vector predictor output. One input is the a functional control history, and the other input is the current state. So since you're mapping the current state, the mapping will be accurate only for states that are as large as those for which you train it. And you cannot train a neural operator for an unlimited size of the state. So this result, when I say that it's semi-global, mathematically, this should be read as follows. That for any size of anticipated closed loop states, there exists a neural operator that is large enough and produced with a large enough number of training runs, such that in closed loop, with initial conditions restricted in this manner, where omega is explicitly given in terms of both the accuracy and the size of the training set, in terms of both the functional inputs and the vector inputs, if the initial state is no greater than this estimate, then this result is obtained. So two limitations. One is the semi-globality, namely the requirement to need a large network for large initial conditions. And the second thing, that no matter how accurately you train it, you're always going to have a residual error because it's an approximation of the feedback law, not of a feedback gain.
The question. Thank you for the presentation. Regarding the RSM model, I have a question for the regularity of either the control of the state. Do you assume that is, for example, PV, do you rely on L1 estimates, for example? Because I saw, for example, in the beta, it was in infinity more than that.
Right. So the stability results for the state are, I think, in the H1 sense. These are results by a former student of mine, not my results. So these are results from Huan Yu and her team at Hong Kong University of Science and Technology. So my recollection is that the results are in the H1 sense.
Okay, thank you very much.
Yes, it seems to have.
Miroslav, if I understand correctly, the methodological tools to this convergence is you have initially the control system with the feedback law, and it is just perturbation, robustness of this stability. Okay. And then depending on what kind of approximation you do, you have more and more destabilizing disturbances.
Yeah.
Now, what's about finite time convergence? So if you take a feedback that stabilizes in finite time, okay, and you try to approximate as you did with the neural network that introduces a perturbation.
Yeah.
Do you know any scheme that preserves finite time stabilization, or you just get this practical stabilization for finite time?
I think it's a wonderful question and a wonderful thing to do. The very first result, in the absence of the perturbation, was a finite time result, and my guarantee was an exponential result. So I lost the finite already at the very first step. But I wasn't even trying, so I'm not sure.
Like sliding mode control. I'm not thinking about this transport equation. Like in sliding mode control, the design. For instance, are these neural operators that you never showed, by the way? You remember that in sliding mode, they have this homogeneous property that they use all the time in order to design feedbacks. These neural operators, do they preserve homogeneity or not at all?
I haven't looked at this kind of feedback, but
not at all.
You could once you think about this. I have not actually looked, even in the absence of neural operators, at fully general finite time homogeneous feedback laws. I've looked together with Andrei Polyakov into delay compensation in the presence of finite time stabilizing homogeneous feedback laws for linear systems. That's without the operators. Will this be preserved? I have no idea. It's so hard even without the operator. But you said something that's very important. This all looks like robustness analysis. It's true. What's really interesting here is not that. That's not new. We've studied robustness of PD control. What's new is the question of establishing continuity and Lipschitzness of these PDs. And they're always different. This is what's mathematically new. And I showed you only 2% of my talk was dedicated to that, and it was on a trivial convolution. But that is why I'm drawn. That is the part worth doing.
Thank you. So there's surely more questions that can be asked at the coffee break.